I recently read an article from Chris DeDecker on Low Tech magazine that discussed some of the costs associated with solar energy production and storage. They argue the cost of the battery and charging circuit is by far the most expensive component to purchase and to maintain throughout the lifetime of a PV setup. They also draw attention to the energy requirements associated with manufacturing these storage components. In order to minimize costs and increase sustainability, then, we should only use the solar power when the sun is shining and to not store power at all. That got me thinking though. There are lots of ways to store power, not just with a battery. The basic design presented in this video is a low-cost, low-complexity battery that uses 2 water reservoirs and a solar-powered pump. This is essentially a 2-part circuit. We have our battery circuit, which consists of a rain barrel, which stores water at an elevated location, a small hose, and a lower reservoir. Water will return from the lower reservoir to the upper reservoir through a solar-powered pump, which will only activate during the day. The second part of the circuit is the electricity generator. This is a simple water turbine spinning an electric motor. I'm sure similar projects like this have been done. Certainly home hydroelectric systems have been built before, but I wanted to give my idea a try. The first part I decided to tackle was actually the power generation component of this. I figured that this would be the most complicated and require the most components. This would be a good proof of concept for me to figure out if I could pursue this idea. Converting rotational energy into electric energy is a fairly trivial matter. We can accomplish this by turning the shaft of an electric motor. We have 3 different kinds of motors to choose from, either brushed to DC motors, stepper motors, or brushless. All these will work, but they will all require slightly different circuits. After researching it a little bit, I decided that I would go with a stepper motor as the basis for my power generation. The stepper motor provides a good balance of simplicity for components and also a good amount of power generation. The stepper motor circuit requires building a full bridge rectifier as well as some sort of DC power regulator. I bought a simple one off of Amazon for several bucks. The most complicated component of this, for me at least, was the structure of it. As I might be the last maker on Earth who does not have a 3D printer, I requested my friend to make a simple water wheel for me so that I could start prototyping things. I made a very rough model out of cardboard to figure out dimensions, then moved over to a piece of plywood that I had lying around. Warning, the views of this prototype are incredibly jank. If you're sensitive to such things, you may want to avert your eyes. But with all these things put together, and a simple V-belt strung between 2 pulleys and the motor, I could verify that yes, we do in fact get voltage. Another thing to test was the reduction ratios between the gear diameters. The principle here is the exact same as bicycle sprockets. A larger driving wheel and a smaller driven wheel will result in more speed at the expense of torque. An equal diameter driving and driven wheel will have a balance between these 2 forces, and a smaller driving wheel and a larger driven wheel will have more torque at the expense of rotational speed. I found that having a large sprocket on the water wheel and a small sprocket on the stepper motor required way too much torque. It made it very difficult to move, even with my own hands. At this point, I decided to go with a small sprocket on the water wheel and a large wheel on the motor. I wasn't able to test it under running water, however. I decided to rectify the janky situation and have these parts laser cut out of a more sturdy material, and to make it look a bit more pretty. I made a basic design that followed my prototype. I added an idler wheel to the design so I could be more flexible with reduction ratios. This was the first time I've used a laser cutter, and there was a bit of figuring out how to format the SVG file to actually work with the software. I went ahead and cut the final design from 1/4" MDF with great results. I had to widen the holes for the bearings slightly, as they were exactly the same as the bearing outer dimension. That's laser precision for you, I suppose. With all that, I put it together for the first test, and wouldn't you believe it? This is the first test. This isn't working at all. It's too much friction. I think I might need a bigger wheel. That sucks. A spectacular failure. The wheel tries to move for a brief moment, but doesn't yield. There are multiple points of improvement here. For one, a larger wheel with larger paddles for more torque. Another, I think there was a little friction between the wheel and the uprights, so the wheel could be a bit more narrow. I could also add a flywheel to give the whole design a bit more weight. Of course, that would require a little bit more torque to start it, but I'm not opposed to giving the whole wheel a hand start. And perhaps the water needs to fall from a greater height in order to impart more energy on that. I'm still not sure what the energy yield of this idea is. This is not the end of this project, but it's getting into fall, and I don't want to start dealing with freezing temperatures. I'm publishing this video and project in the spirit of the Done Manifesto, specifically the principle of, if you can't build it, share it. I'm excited by this project and I want to work on it more, but time got away from me once again while I had good weather for it. I'm still finding my maker groove. Let me know what you think though. What do you think went right and went wrong? Do you think this project has any potential?